Hello students, welcome back to part 2 of our lesson on current electricity. In the previous class, we learned about Ohm's law and resistance. Now, let's move forward to combinations of resistors and the effects of electric current. When we connect multiple resistors, we can do it in two main ways, series or parallel. In a series combination, the same current flows through each resistor, but the voltage divides across them. The total resistance is simply the sum of all resistances. Our equivalent is equal to a 1 plus, a 2 plus, a 3 and so on. In a parallel combination, voltage remains the same across each resistor, but current divides. The total resistance is given by 1 divided by our equivalent is equal to 1 divided by our 1 plus 1 divided by our 2 plus 1 divided by our 3. Example, if we connect 2 ohms, 3 ohms and 6 ohms resistors in parallel, 1 divided by R is equal to a half plus 1/3 plus 1 divided by 6 equals 1. Therefore, the equivalent resistance is equal to 1 ohm.
Sir, may I ask a question? Why is the voltage the same across each resistor in a parallel connection even when the current divides?
Good question. In a parallel circuit, all resistors are connected directly across the same 2 points of the circuit. That means each resistor experiences the same potential difference. However, current divides based on resistance. The smaller the resistance, the larger the current passes through it. When current flows through a resistor, a portion of the electrical energy is converted into heat. The heat produced is given by H is equal to I squared R into T, where I is the current, R is the resistance, and T is the time. If 2 amperes of current flow through a 5 ohm resistor for 3 minutes, then the heat produced is equal to 4 times 5 times 180 is equal to 3600 joules. This principle is used in electric irons, kettles, and heaters. In an electric bulb, current heats the filament, usually tungsten, until it glows. This process is called incandescence. Let's work on electroluminescence, where current causes certain materials to emit light without much heating. Now, let's move to understanding the magnetic effect. The magnetic effect was discovered by Hans Christian Ørsted. He found that a current-carrying conductor produces a magnetic field around it. According to the right-hand thumb rule, if you hold a wire in your right hand such that the thumb points in the direction of the current, then the curled fingers show the direction of the magnetic field. This effect is the basis of electric motors, electromagnets, and generators.
Sir, can I ask one more question? Why does the direction of the magnetic field change when the direction of the current is reversed?
Excellent observation. When the current reverses, the flow of electrons reverses too. Since the magnetic field depends on the direction of electron flow, it also reverses. That's why we use the right-hand rule to find the direction each time. Power is the rate at which electrical work is done. It can be calculated by P is equal to V multiplied by I, or P is equal to I squared R, or P is equal to V squared divided by R. Power is measured in watts, W, and 1 kilowatt equals 1000 watts. Energy consumed is the total work done, given by E is equal to P times T. Its unit is joule, J, or kilowatt hour, kWh, where 1 kilowatt hour is equal to 3.6 times 10 to the power of 6 joules. Example, a 100 watt bulb used for 10 hours consumes 1 kilowatt hour of energy. EMF is the maximum potential difference provided by a cell or battery when no current flows. It's represented by epsilon. When current flows, the voltage available across the terminals becomes slightly less due to internal resistance, R. So, the terminal voltage is given by V is equal to epsilon minus I into R. In complex circuits, We use Kirchhoff's laws to analyze current and voltage. Kirchhoff's current law, also known as KCL, says the sum of currents entering a junction equals the sum of currents leaving it. Sigma I in is equal to sigma I out. Kirchhoff's voltage law, KVL, the algebraic sum of all potential differences in a closed loop equals 0. Sigma V is equal to 0. These laws are extremely useful for solving multiloop circuits. Let's look at some simple examples to apply these concepts. Example 1. Find the current when 12 volts is applied across a 4 ohm resistor. Solution: I is equal to VR is equal to 12 divided by 4 equals 3 amperes. Example 2. Find the heat produced when 2 amperes of current flows through 5 ohms for 3 minutes. Solution: H is equal to I squared R into T is equal to 4 times 5 times 180 is equal to 3600 joules. Example 3. A 100-watt bulb is used for 10 hours. Solution: energy is equal to power times time is equal to 100 times 10 equals 1000 watt hours is equal to 1 kilowatt hour. So, students, today we've covered a complete overview of current electricity. We learned about resistor combinations, heating and lighting effects, EMF, power, and Kirchhoff's laws. Revise these formulas and practice the numerical problems. They are scoring and conceptually important. Thank you for your attention. Keep learning. Stay curious. Jai Hind.